Okay, so here I'm going to show you how to access D-Wave solvers. And it's, before you try to do any of this stuff on the D-Wave, first you need to set up the SSH tunnel, which gives you access to the real hardware. And then depending on your settings, you may need to do this export -n HTTPS proxy so that you can access the solvers. So the first thing to do is that you might want to do is to access the local solver. So the local solver is D-Wave simulator. It's sort of like a 128-bit D-Wave machine. At least that's what it's supposed to be. And you sort of access it by calling this D-Wave SAPI 2.local, and then this local connection, and then finally get solver. And then you just give it the name of the solver, C4 SW sample. So once we have the solver, then we can access the adjacency information related to the solver. So we run this code, util.getHardwareAdjacency, and then we pass it the solver, and it gives us this data structure that I've called local adjacency, which looks like this. It is a set of tuples, so as a Python object, it is just a set, and it contains tuples. So basically what this means is that there's a bit in this solver that is denoted by index 127, and it is connected to the bit denoted by index 119. So bit 127 is also connected to bit 120, 121, 122, and 123. So sometimes when you're building up problems on the D-Wave, it's good to know what the adjacency information is so that you can build a problem that will custom fit on the D-Wave. Or if you're not interested in setting up problems that are a natural fit for the D-Wave, you still need this information if you want to embed a problem onto the D-Wave. All right, so that is the local solver. The hardware solvers are more interesting, and in order to access the hardware solvers, you're going to need a token. Here I've just put some text in here that you should replace it with your own token, but I've already set up a variable called myToken that has a valid token in it. So if you want to access these so-called remote solvers, which are like the real hardware solvers, the first thing you need is this remote connection. So we run this code, we get the remote connection. Again, it's some Python object. It's not really that interesting. The first thing you might want to do with it is to run this function, remote connection.solver names. And then we can look at the names of the solvers that are available to us. So right now there's two solvers available, DW2X underscore VFYC, that's the so-called virtual full yield solver, and then the DW2X, which is sort of like the raw hardware. So the idea of the virtual full yield solver is that the DW2X is missing some bits, but the virtual full yield solver is sort of meant to be like a version of the chimera graph that isn't missing any bits. All right, I personally have never used the virtual full yield solver, so let's just get the DW2X. So again, we sort of go in the same way. We call this getSolver function, except now instead of doing the local connection, we use the remote connection, and we call it DW2X solver. And again, it's a Python object. It has some properties, but generally they're not that interesting. And again, we here will get the adjacency information for this as well. Now DW2X adjacency. It's a much bigger set, but it sort of has the same format. It is also just a Python set, and it's a set that contains a bunch of tuples. And basically, if you see a tuple, like for instance 948, 940, that means that bit 948 is coupled to bit 940. Okay, so that's how you'd access the solvers. And then once you have access to these things, then you can actually use the solvers to try to solve some problems. Okay, so now that we've looked at how to set up the solvers, the first thing we're going to do is to try to solve what is probably the simplest problem you could try to solve on the D-Wave. And we're going to basically use it to do coin tosses. So the first thing you need to do to be able to solve problems on the D-Wave solvers is to import this part of the SAPI D-Wave underscore SAPI2.core. I just call it core. And then I'm going to run the file I had set up before that sets up all my solvers. And now we should have the DW2X solver like we had before. So the D-Wave solves problems that can be thought of either as QUBOs, which are quadratic unconstrained binary optimization problems, or as Ising problems. So here I'm going to look at an example of a QUBO, which I'm going to call Q. So I define this QUBO Q, and the way that these QUBOs are structured in Python for the Python SAPI is that they're dictionaries, and the keys of the dictionary are tuples, and then the values are just numbers. So what this Q basically says is that there's one bit in my QUBO, and the only bit I care about is the 0th bit, and I should provide a weight to the linear coefficient in this QUBO of the 0th bit of 0. So essentially that's sort of setting up or trying to set up a fair coin toss. And now we can use the solver to actually solve it. So we got this thing answer. Let's talk about how this call goes first. So core.solve QUBO, the first thing you pass it is the solver. The next thing you pass it is this dictionary Q. And then there's a number of optional parameters you can give it, num reads, how many samples do you want from the machine, and the SAPI has this feature of auto scaling. So the keys, like this part of the Q, the keys in here have to be bounded in some way, and the SAPI gives you the option to sort of restructure your QUBO so that all those values in the Q are within the appropriate bounds. But here we set auto scale equals false, so we're saying, don't do that. And since our only coefficient here is 0, we're not going to run into any problems. Okay, so what does the answer look like? So the answer is just a Python dictionary, and we can look at what the keys of it are. So it has 4 different keys: timing, energies, num occurrences, and solutions. So if we look at, let's go through these one by one. So the timing just breaks down how the time was spent in solving this problem. It has anneal time per run, post-processing overhead time, etc. All these other timings. Then there is the energies, which gives you the energies of your QUBOs, and this also tells us that it found 2 different solutions, which we should expect in this case. So the 0th bit can either be 0 or 1. It found both of those possibilities, and since our coefficient is just 0, 0 times 0 is 0, 1 times 0 is 0, so the energy of both of these things is 0. So we can also look at the num occurrences, and this is basically saying that the first solution happened 7 times and the second solution happened 3 times, and finally, the most interesting part is probably the what do they call it? The solutions. So if you look at this, it looks like a lot of 3s. And if you look back at our Q, you see that there's only one bit that matters in our Q. And it's the 0th bit. So let's look at only the 0th bit of the 0th solution. So this is saying that this first index here basically gives the solution number, and then this second index gives the bit within the solution. So we're saying in the 0th solution, show me what the 0th bit is, and in this case it's a 0. So now let's look at the next solution of the first bit. It's a 1. So the 2 solutions we got, the only bit we care about, one of the solutions is 0, one of them is 1. If we looked at another bit, say the first bit of the first bit of the first solution or the second bit of the second solution, depending on how you want to count, is a 3. And if you look at practically all the bits of the solutions they're 3s, except for the first bit. And 3 is sort of D-Wave's secret code for saying this bit wasn't part of Q. So like the first bit, since it's not part of Q, will be 3. The second bit will be 3. Only the 0th bit will be not a 3. So when you see a bunch of 3s in there, that's just the bits that weren't part of your QBO. So let's just run through this and print out some information. So yeah, we got two different solutions. The first bit was either, or the 0th bit was either 0 or 1. We got 0 7 times and 1 3 times, and both of them had 0 energies. So here, you know, we were trying to toss a fair coin. 1 was 7. We got 7 zeros and 3 1s. You know, you might expect to get 5 5, but it doesn't always go that way. Let's try to turn up the number of reads and see if we can get something that's a little bit more fair. So now I'm just going to run all this code at once. Exec file coin toss. And let's see what we get. So sometimes it takes a minute because you have to, you know, send this problem off to the D-Wave, download the results, and do all that stuff. So in this case, with 1,000 runs, actually there were less zeros and more ones, 467 zeros and 533 ones. So it seems to be, you know, roughly a fair coin, you know, within some tolerance. And that's how you would solve a simple coin toss problem on the D-Wave. Okay, so now we're going to look at another coin tossing example, except in this case, since D-Wave's or LANL's D-Wave machine has a little over 1,000 bits, instead of tossing one coin at a time, we're going to toss a number of coins equal to the number of bits on the machine. So to get started, we do the same thing we did before. We import the SAPI 2 core, and we execute the setup solvers code that we looked at earlier. Okay, so the next thing we need to do is to go through this adjacency. If you remember, we had this variable dw2x adjacency. Which is a set containing tuples that tells us the bits that are interconnected. We don't actually care about the bits, for the coin tossing problem, we don't care about the bits that are connected to each other, we just want to know which bits are there. So the way I do this is I create this set called live bits, and the set is going to contain the bits that are coupled to at least one other bit. So we just iterate through this dw2x adjacency structure, and we just add, and you know, we get the I and the j out of it, and we add I and j to our set, and once it's done, live bits is a set that just contains all the bits that are actually working. So for instance, you'll notice that bit 1043 is missing because that's just not a working bit on the hardware. All right, so the next thing we're going to do here is, in this case, we're not just going to look at a fair coin, we're going to look at two coins, one coin that's a fair coin and one coin that's sort of an unfair coin that is biased in some way. And the reason I wanted to do this was just to highlight this function here, async solve QBO. So for the first coin toss example we looked at, we called this function core.solveQBO, which basically returned us some data structure that told us about the timing, the energies of the solutions, the number of occurrences of the solutions, and the solutions themselves. This time we're going to use async solve QBO, and that doesn't tell us anything about what the answers are. It just gives us this thing, basically a data structure that denotes that a problem has been submitted, and then later on we're going to wait for those problems to finish, and then finally here in this line we're going to actually get the results. But let's start by submitting the problems. So we ran that here. Again, we have this here we have this loop for j in range of 2. This is just saying for our two coins, one that's fair, one that's unfair. we create a cubo, which again is a Python dictionary where the keys are tuples. And then finally in this loop, we loop through all the live bits, and then we add a term to our queue for bit I. So when you have the tuple II, that basically means a linear term in the cubo. And here we do 0.5 times j. So on the first time through this loop, j is going to be 0, so all the terms in our queue are going to be 0, which basically means a fair coin. The second time around, j is going to be 1, so all our terms are going to be 0.5, so that's going to bias our coin. The next thing we do is we call this async solve cubo. The format, the calling sequence is similar to just solve cubo. First you pass it the solver, and you pass it your cubo, and it has all these optional arguments. Num reads, here we set it to 10, auto scale we set false, annealing time is 200, and the units here are microseconds, so this is a annealing time of 200 microseconds. So we submitted those problems. Now when you're using this asynchronous API, before you try to access the problems, you should first wait for them to complete. So in this case, we call the function core.await completion, and we created this list submitted problems that contains the 2 problems that we submitted. So this is basically saying, wait on these 2 problems. The second argument specifies how many problems have to finish before this await completion function should return. So in this case, we're saying, let's wait for both of them. And then this third number is a timeout, and this number is in seconds, so we're saying, don't wait more than a minute. In this case, since we actually waited a long time to call the await completion function, they were ready to go as soon as we called it. So now that we've waited for the problems to finish, we can call the submitted problem.result to actually get the results of the problems. And here this loop is just going to go through those 2 problems that we submitted and tell us a little bit of information about them. So let's start at the top. So the timing information, it's not that interesting. Anneal time per run, if you remember, we set to 200. There's a lot of information about other timings in there. So we requested 10 samples. In this case, each solution occurred 1 time. So if we have this num occurrences thing in our answer, so when you toss 1,000 coins, you wouldn't expect them to sort of get the same sequence of heads and tails twice. So we don't get that here. Every solution is unique. They all have 0 energy because basically our cubo that we gave is just 0. Okay, now maybe the more interesting part, the fraction of the bits that are 1. So you can see for all 10 answers that it got, something close to 50-50, so it's not too bad of a fair coin in this case. Okay, so now let's look at our second solution. Again, the timing information. Now this was the biased coin, and in this case it was biased towards 0. So this problem only got 5 different unique solutions. The first solution occurred 6 times. That's what this 6 is. The other solutions occurred only once. The energies for the solution, the one that occurred 6 times had energy 0, so this is the one where they were all zeros, meaning every Q that came back from the machine, every bit that came back from the machine was a 0. The others were a half, and that basically means that one of the bits was not 0. And then this is just looking at the fractions that were 0. So again, as I guess, the one that occurred 6 times was all the bits were 0. That's not surprising. That would be the most common because it's biased towards that solution. And then these other ones all have the same number of 1s, which is 1, and they occurred once, and energy is a half. So that is how you would solve problems using the asynchronous API. It's really useful if you need to solve a lot of cubos. You can just send them off to the machine, continue doing some processing in your code on your laptop or whatever machine you're accessing the D-Wave from, and then once you're ready to actually look at the results, you can call this await completion function, and then once that's finished, you can just access the results using submitted problem.result. Okay, so now we're going to look at a more complicated problem, and this problem is coloring the map of Canada, which is one of the standard problems D-Wave uses in their training. And we begin, as before, importing the core part of the SAPI, but this time we're also going to need to import one more thing, which is the embedding part of the SAPI. And the reason we need the embedding is because now we're going to have a problem where the quadratic terms in our QUBO don't really match the couplings in D-Wave hardware. And the idea of the embedding is to sort of represent each physical bit, or each bit in our logical problem, as several physical bits, and this will sort of give us a way to get couplings that might not otherwise be available to us. And we do as before. We execute the setup solvers code to get all our solvers. All right. So when you're working with these problems that don't really have the right structure needed to fit on the D-Wave, there's this concept of the virtual QUBO. And for me, when working with Python with virtual QUBOs, a function like this I think is very handy. It's called add to Q. And the idea behind it is that if you have a QUBO Q, this function add to Q will add a term to your QUBO where the coefficient for the term is this V, and then the I and J basically specify which bit you're adding it to. So for instance, if I is 1 and you don't specify J, add to Q would add a linear term to the QUBO where logical bit I is being multiplied by V. And if you specified both I and J, then you would be specifying a quadratic term, and it would basically be saying you'd be adding V times Q sub I times Q sub J. And this function just sort of makes it easy to manage those things. So if we're going to color the map of Canada, first we need some information about the map of Canada, and this is how we're going to represent it here. So this provinces is just a list of 2-character strings that specify all the provinces like British Columbia, Yukon, and so on. We also need to consider our set of colors. Here we're going to use 3 colors, red, green, and blue. And the idea of this map coloring is to assign a color to each of the provinces such that no 2 neighboring provinces have the same color. So if we're going to do that, we need to know something about who's neighbors with who. So we have neighbors be a Python dictionary, and if you specify, so our keys will basically be these 2-letter codes that we use to specify the provinces, and then the values of this dictionary is a list of neighboring provinces. So for instance, the neighbors of British Columbia are Yukon Territories, Northwest Territories, and Alberta. And then again, when you're dealing with these virtual QUBOs, it's often handy to have this idea of an index map. So, the D-Wave, and the way that D-Wave wants their QUBOs to be structured is that the bits are sort of, thought of as tuples of indices, or the coupling, the bits have indices associated with them, but, for us it's easier to think about the bits being associated with provinces and colors. So the idea is each province will have 3 bits associated with it. One of the bits should be 1 if the province is colored red, another bit should be 1 if the province is colored blue, and the other bit should be colored 1 if the province is green. And so if you sort of think about a matrix of where there's 1 row for each province and there's 1 column for each color, that's sort of the bits that we're going to be having in our virtual QUBO, and we sort of want to be able to access those bits in terms of provinces and colors. So the idea of the index map is that it's a dictionary, and it takes as a key both a province and a color, and what it gives out is an index. And so basically what we can do is think about the bits in terms of provinces and colors, and then this map will tell us or this dictionary will tell us what bit that corresponds to in sort of the linear index that D-Wave wants. All right, so the next thing we're going to do is create this dictionary that's going to represent our virtual QUBO. So we have virtual Q as just an empty dictionary at the moment. And I'm not going to go into the details of how you would construct a QUBO to solve the map coloring problem, but I'm just going to copy and paste the code that does it and sort of explain it at a very high level. So here, this set of nested loops basically adds penalties so that each province hopefully gets assigned only one color. So you don't want to assign provinces 2 colors, you don't want to assign provinces 3 colors, you don't want to assign provinces 0 colors, you want to assign them only 1. And this loop basically adds terms to our virtual QUBO that encourages the D-Wave machine to do that. The next thing we need to do is add terms that will prevent encourage the D-Wave to not assign 2 neighboring provinces the same color. So again, we have some nested loops here. We go over the provinces, and then you can see there's this thing here. If they're neighbors, we add some terms to our QUBO, and this term will sort of penalize bit values that have neighboring provinces being assigned the same color. Okay, so that's, in a perfect world, that would be everything we need to do. And we could just move on straight to solve QUBO. But if we try to do that, if we try to run this code, answer equals solve QUBO, dw2x solver, and then virtual Q, it actually fails. And the reason why it fails is because, there's quadratic terms in our QUBO where D-Wave hardware doesn't have a coupler. So the idea to get around this is to use the embedding part of the SAPI. So this code computes it finds an embedding. You just do embedding.findEmbedding. You give it the keys of the virtual QUBO. So it's basically a bunch of tuples that say, in my virtual QUBO, which bits need to be connected, and then you give it the dw2x adjacency, which says which bits are actually coupled on the hardware. And then the next thing I'm going to do is go from QUBO world to Ising world. So again, the problems on the D-Wave can be thought of as either QUBOs, quadratic unconstrained binary optimization problems, or Ising problems. And so what's actually being solved on the hardware is an Ising problem. And I'll explain in a minute why we're going to switch to Ising. But basically, they're equivalent. You can switch between QUBO and Ising. There's no problem. There's this function util QUBO to Ising that does it for us. And we get back this virtual H, virtual J, and this Ising offset. So there's some energy offset between the Ising and the QUBO. But it's not something we need to worry about here. All right, and the next step is to actually embed the problem. So we call this function embedding.embed problem. We give it the virtual H, we give it the virtual J, we give it the embeddings that we found with the find embedding function, and we give it the dw2x adjacency information. And then what it gives us back is H, which is sort of the new H in our Ising problem, but one that respects the D-Wave hardware. It gives us J, which is the new J in our Ising problem, and it respects the D-Wave hardware. And then they give us this JC, which basically gives us information about, going back to this idea that multiple physical bits are representing one logical bit in our problem. This JC basically tells us information about which bits are being, or which bits need to be chained, it's called, so that they can represent the same bit in our logical problem. And then it's possible that this embed problem could change the embeddings depending on certain optional keyword arguments that you give to the embed problem. Okay, so after we do the embed problem, we're not quite done yet. We still need to actually modify our J so that we sort of encourage these bits that are part of, the collection of physical bits that represent a single logical bit need to be encouraged to take on the same value. And we use this JC, the chain part of the J. We iterate through the keys, and we see if JC is -1. So if JC is -1, that's like the secret code that says this coupling is parts of a chain. So basically it means these two bits are part of the same, these two physical bits are part of the same logical bit, and then we just have to set our actual J in our real Ising problem to take on some value that encourages it to make these bits take the same value. Okay, so we finally have our H and our J that we can work with, and we are ready to solve the problem. So we get our answer. Here we call core.solve Ising. Again, we give it DW2X solver, H and J. We give the num reads. There's different optional arguments you can specify. I'll just note that here we did not specify whether or not to auto-scale. So auto-scale defaults to true. In this problem, we're going to use the auto-scaling. And so now we have our answer, but it's sort of, the answer we have is like living in this embedded world where multiple physical bits are representing our logical bit. So we need to do this unembedding process to get back to our logical world. So we call this function embedding.unembed answer. We pass it answer of solutions, and we give it the new embeddings that came from this embed problem. And this also has several optional arguments. Here, the only one I'm specifying is broken chains, and I choose the option weighted random. Basically what this means is if you have multiple physical bits representing one logical bit, what it does is it randomly picks one of those bits and it assigns the logical bit the value of the randomly selected physical bit. All right, and so the answer we got here is like an Ising answer. I prefer to think in terms of Cubo, so I'm just going to map back to Cubo world. So this function right here, 0.5 times y plus 1, basically maps you from an Ising solution of plus or minus 1 to a 0, 1. That's used for the Cubo world. All right, and last but not least, well, I guess not quite last, but there's this function check answer, which looks through the solutions. It sees it wants to check to see that it only got assigned one color, and it wants to check to see that no two neighboring provinces got the same color. And if it's all good, it just prints all good. So let's look through each of our solutions and see what happened. So you can see at the bottom, some of them are failing, but most of the early ones, it's all good. They passed the test. They were valid map colorings. You can see in this one, Northwest Territories and Alberta got the same color. In this one, Yukon got assigned no colors. And you can kind of look at what's going on with these different solutions. But this is sort of how you might go about coloring the map of Canada using the D-Wave, or just more generally how you could use virtual cubos and embedding to solve logical problems that don't naturally fit on the D-Wave.